All right, let's go ahead and go over these solution stoichiometry notes. And this is the stoichiometry part of this unit. It's very easy. The thing we need to keep in mind is that the molarity equation can be rearranged to solve for moles. And once you have moles of one substance, you can convert to moles of another substance. And so that is how you do that. So again, once you've determined the number of moles that's inside of a solution, you can then perform stoichiometry calculations to determine the amount of moles or grams or volume of gas or particles or whatever of reactant or product that you are trying to calculate. So let's go ahead and practice some of this. So if you take a look here, it says, what is the molarity? Okay, so it's asking for molarity of a solution if 0.8 liters were used to react with this many grams of sodium carbonate. And so, again, what it's asking for the molarity of HCl, and molarity is equal to moles divided by liters. Well, if you take a look here, these are the liters, and we just plug in the liters. And once we plug in the liters, the only other thing we need, so here's the liters, the only other thing we need is moles. So we don't have moles of HCl. And so again, we're looking for the molarity of HCl, but we don't have the moles of HCl. So how do we get the moles? Well, look what it gives us here. It gives us 21.2 grams of the sodium carbonate. And we can go from grams of sodium carbonate to moles of sodium carbonate. And again, once we have moles of one substance, we can convert it to moles of another substance. And once we convert it to moles of HCl, we can then plug it into there. And it's that simple, so let's go ahead and do this. So we have 21.2 grams of NaCO3, Na2CO3, and we're going to go from grams of NaCO3 to moles of Na2CO3. And then we're going to go from moles of Na2CO3 to moles of HCl. And we can see from the balanced chemical equation that 1 mole of this will react with 2 moles of that. This fraction here, we use the molar mass, which we get from the periodic table. And what we end up with is 106.005. And I did use a periodic table that doesn't have the same molar masses as your periodic table. So your decimal might be a little off, but that's okay. So anyways, you type this into your calculator, and you end up with 0.400 moles of HCl. And again, once you have the moles of HCl, you can just plug it into the molarity equation. So I'm going to go ahead and clean this up here. So we know that molarity is equal to moles of HCl, which we just calculated. It's 0.400 divided by the liters, which is 0.8 liters, and you can see the molarity is equal to 0.5 molar. And so the solution is a 0.5 molar HCl solution, and this is our answer. So again, just to recap, it's asking for molarity, and the two things we need are liters and moles. It gave us the liters, we had to calculate the moles, and it's that straightforward. So let's go ahead and do the next one here. So this one is giving us liters, and it's giving us molarity of HCl, and it's saying it's reacting with excess sodium carbonate. Now this is asking for what volume in liters of carbon dioxide gas would be produced. And so this is at standard temperature and pressure. So this actually is a solution stoichiometry problem, and it is a gas stoichiometry. So the first thing we need to do is we're going to take the molarity equation. And so real quick, what it's asking for liters of this. And so we're going to take our molarity equation, which is equal to moles over liters. And what we're going to do is we're going to calculate moles of HCl. And once we know moles of HCl, we can then convert it to moles of CO2. And then we can go from moles of CO2 to liters of CO2, because if we remember from last unit, 1 mole of any gas at standard temperature and pressure is 22.4 liters. And so that's how we're going to go between moles of carbon dioxide and liters of carbon dioxide. So the molarity equation, if you rearrange it, the moles will be equal to molarity times liters. And so that's going to be 5 times 1, which is going to be 5 moles of HCl. And then we can go moles of HCl to moles of CO2. And then we can go moles of CO2 to liters of CO2. And we can see that this is a 2-to-1 ratio. We know that 1 mole of any gas is 22.4 liters of that gas. And then you just type that in your calculator, and you end up with 56 liters of CO2. And that's it. So one thing that I really want to point out here is this 1 mole is 22.4 liters. This is specifically for a gas. You cannot use this for aqueous solutions or for liquids. You can only use it for gases. So when we're dealing with liters of a solution, we deal with the molarity equation. So again, this right here, very important. Just keep in mind that that has to specifically do with a gas. And yeah, so let's go ahead and go to the next one here. It says in a neutralization reaction, 100 milliliters of hydrofluoric acid solution reacted completely with 600 milliliters of sodium hydroxide, and it says calculate the molarity of HF. So first thing we need to do is write a balanced chemical equation. So it's this plus sodium hydroxide, and we'll learn how to write these equations next unit. It's an acid-base reaction, and you can see it's all a 1-to-1 ratio, so that's nice. Now this particular problem, it's wanting us to calculate the molarity of HF. So again, molarity is equal to moles divided by liters. And if you take a look, it gives us the milliliters, which we can convert to liters. It's the same thing as 0.100 liters. And we just plug that in there. So what we would need is the moles of HF. And again, this is dealing with HF right here. So we would need the moles of HF. But we're not given the moles of HF, but we are given this information right here to where we can calculate. So again, we can use the molarity equation to plug this into here, and then plug this into here, and we end up with 0.5. Now remember, this is liters, so you have to convert the 600 milliliters to liters, so that's 0.600, and then we rearrange this, and you end up multiplying these. And what you end up with is 0.3 moles of sodium hydroxide. And then we can just go from moles of sodium hydroxide to moles of HF. And it's a 1-to-1 ratio from the balanced chemical equation, and that means it's 0.3 moles. So it's the same number of moles there. And once we have our moles of HF, we can then plug it into this right here, and that will give us our molarity of HF. So again, molarity of HF is going to be equal to the moles, which we just calculated is 0.3, divided by the liters, which is 0.1, and what you end up with is a 3 molar solution of HF. And that's your answer. And smiley face. And that's it. So that's all there is to it. It's really easy. Something to keep in mind, what you really want to keep in mind when doing this is you want to remember, this equation. I would just write this equation down, and I would think about what is it asking me for. In this situation, it's asking me for molarity. And what do I need to calculate molarity? Well, I need moles of HF, and I need liters of HF. And so you then realize that you have to calculate the moles of HF to be able to plug it into that equation there. So again, when in doubt, convert things into moles and you'll be good. So this is, it's not too bad. We'll do more practice problems with this in class. You have a great day and take care.